Welcome to Brain Vision.
Okay, so we want to calculate the radii of Rigel star, and then we also want to look at that for Procyon. Okay. All right. Now, in this question, we are going to employ the formula H is equal to A multiplied by E times Stefan Boltzmann's constant multiplied by the thermodynamic temperature to the power 4. Okay, now in this question, we've been asked to assume that these stars are spherical in nature. All right, so if they are spherical in nature, then what are we going to say about that? Since we are looking at radius, then meaning we need to look at the area of these stars by considering the formula for calculating the area of a sphere. All right, now the area of a sphere is usually given as 4 pi r squared. All right, now the temperature of this star is given us 11,000. Is given us 11,000. I beg your pardon, 11,000 Kelvin. That is the temperature of the Rigel star. Okay, so let's go ahead and calculate that, and let's see what we'll get for that. Okay, so first and foremost, we've been given the heat energy, or the rate at which heat energy is generated from that body, to be given us 2.7 times 10 to the power 32 watts. That's the rate at which heat energy is given from that star. All right, so this is actually H that we are looking at. This is actually H. Okay, so let's go on and factor this into our equation, and let's see how best we can look at this. Now remember, the question also tells us to take the emissivity to be equal to 1. And then we are also looking at Stefan Boltzmann constant to be equal to 5.67 times 10 to the power negative 8 watts per meter squared per Kelvin to the power 4. All right, so let's go ahead and look at this. Okay, so we can say that, let me scroll up a bit. We can say that 2.7 times 10 to the power 32 is equal to the area, which is 4 pi r squared, the area of a sphere, multiplied by Stefan Boltzmann's constant, 5.67 times 10 to the power negative 8. All right, now multiplied by the thermodynamic temperature to the power 4. Now remember, emissivity is 1. All right. So in this situation, when we simplify or we evaluate, let's do this step by step. So we can say that making the radius the subject, we have r squared being equal to, and then evaluating all other figures that we have in this equation, we'll arrive at, let's say, 2.7 multiplied by 10 to the power 32 divided by 1.04 times 10 to the power 10. And this should be equal to 2.59 times 10 to the power 22. All right. So when we find the square root of this answer, which is 2.59 multiplied by 10 to the power 22. All right. So when we do that, this is going to give us 1.61 times 10 to the power 11 meters. So that is the radius of the Rigel star. Okay, now the second part of the question also says that we should calculate that of the Procyon star as well. So for Procyon, we've been told that its rate of heat energy given out is given us 2.1 times 10 to the power 23. Okay, all right, so let's just go ahead straight away and then let's factor all of these parameters into the equation. Okay, so we have 2.1 times 10 to the power 23 is equal to 4 pi r squared multiplied by Stefan Boltzmann's constant 5.67 times 10 to the power negative 8. multiplied by the temperature for the Procyon star is 10,000. The thermodynamic temperature over this 10,000 to the power 4, and then multiplied by emissivity, which is 1. Okay, so when we do this, we have R squared being equal to 2.1 times 10 to the power 23, all divided by 7.13 times 10 to the power 9. 10 to the power 9. All right, now when we evaluate that, this should give us the square root of 2.9 times 10 to the power 13. So this should give us a radius of about 5.4 times 10 to the power 6 meters. I beg your pardon. Power 6 meters. All right, so this is the radius for the Procyon star. This is the radius of the Procyon star. Now, the radius of the Earth actually is about 6.37 times 10 to the power 6 meters. And then that of the sun, the radius of the sun, is about 6.96 times 10 to the power 8 meters. All right. Now the distance between the sun and Earth is about, let's say, 151.4 times 10 to the power 9 meters. All right. So if we look at this carefully, we can say that the Rigel has such a vast radius. Let me see, the Rigel has a lesser radius than the radius of the Earth, which is also lesser than the radius of the sun, and also lesser than the distance between the Earth and the sun. The Earth and the sun. All right. I beg your pardon. I've said something otherwise. It's rather far greater. Let me rewrite that. Forgive me. It's far greater. The radius of the Rigel star is far greater than the radius of the Earth. I beg your pardon. Than the radius of the Earth, and then the radius of the sun, and then also the distance between the Earth and the sun. I beg your pardon. The distance and the sun. All right. But when we look at that of Procyon is way lesser. Procyon is about 5.4 times 10 to the power 6, which is even lesser than the radius of the Earth, which is really lesser than the radius of the Earth. So what this actually means is that Rigel is such a giant star. It's such a giant star out there that we are looking at. All right.